Hello, everybody. Welcome to the seminar today. I'm very pleased to welcome Érika Roldán from the Max Planck Institute for Mathematics and in the Sciences from Leipzig. Érika will give a talk today on topology of random two-dimensional cubical complexes. So please, Érika.
Thank you so much, Nessa, and I'm very happy to be speaking here at the seminar. Thank you to the organizers to make it possible, and also for the very nice website and all the videos that they share always. Yes, so yeah, I'm gonna talk about some random models, but the random models are gonna be both very geometrical and very combinatorial, and hopefully I'm gonna at the end convince you why it's very interesting to study the topology of these random two-dimensional cubical complexes. And I just want to mention that the paper was published in Form of Mathematics Sigma in 2021. I think I'm missing one there. And it's a joint project with Mathieu Keil and Eliot Paquette. And in the presentation, you will also see some surfaces. And these surfaces is an ongoing project with Dejan Nov and Andrea Beni. And the mathematics visualization that I'm using, I'm developing with my PhD student, Manuel Esteves, at SCATS AI at Leipzig University, where I'm also working. So, okay, so let me start here in the Blackboard that I have. And I want to introduce you the objects that we're going to be working with all the time today. So you know them very well, and it's very easy to we know them since we are in kindergarten, right? So an edge, it's very easy. And then I'm going to put a combinatorial structure so that we can actually keep track of the vertices. Okay, so if I have only two vertices on one edge, I'm gonna assign 0 to one of the vertices and 1 to the other vertex. Okay, if I have a square, well, then I will assign. I need to actually assign now a vector of 2 entries with 0s and 1s, and then I can uniquely assign to each one of the vertices the values, no? So for example, 0, 0, 1, 0, 1, 1, 1, 0, okay? Yes, yes, I'm gonna then say very fast. So if we have an edge, we're gonna assign 0 and we're gonna assign 1 to the other vertex, and then the edge is gonna be labeled with an asterisk. Okay, and if we have a square, then we will assign to each one of the vertices a vector with 2 binary entries, and then it's going to be a unique, and we're going to use all of them. So this is a way of labeling the vertices of the d-dimensional cubical complex. And the d-dimensional cubical complex, the geometric one we know is the interval 0, 1 to the n. Or the n-dimensional. And yes, now there is a very interesting thing that is happening, why I'm using star notation here. And the star notation tells you what is the dimensionality of the phases that we are working with. So in this case, the dimensionality of this phase is 1, so we only have 1 star, okay? And then here, this edge has a 1 star, and you can easily see that actually 1 is common in these 2 vertices, and the entry that changes is 0 and 1, so that's why I'm assigning a star, okay? And so this is a 1-dimensional edge, and then it has only 1 star, and I know exactly which one are the vertices because of the notation, and so on and so forth. So this edge has a star in the first entry because this is the difference between the labels of these 2 vertices, and the same is happening in these 2 edges, and that's why you have only 1 star. And then here you have a 2-phase, and a 2-phase is represented with 2 stars. Okay, so the same will happen if you have, for example, the 3-dimensional cube. Okay, so in the three-dimensional cube, you will represent the three-dimensional cube with 3 stars, the whole structure. And then if each one of the 2 faces, you will need 2 stars, okay? And then I think people love the tesseract usually when I present it. So this is one of representation of the 4-dimensional cube. And then you have tons of 2-dimensional faces that we're going to focus on the 2-dimensional faces. But anyways, you could also represent higher dimensional cubical faces with the notation that I'm presenting. Okay, so the whole structure is represented with 4 stars, and then you can start analyzing each one of the entries depending on the with this notation. Okay, so yes, this is the 4th-dimensional cube in another perspective, right? This is where you will be able to play with the structures. And something that is very important, and it's going to be important for us, is that you have 2 3-dimensional cubes that are parallel. So the idea of having 3 pairs of 4-edge cycles that are parallel in the 3-dimensional cube can also be seen in the 5D cube, because you will have 2 3D cubes that are parallel, okay? And so on and so forth. Here, for example, is the 5th-dimensional cube, right? And then you can see how you have this structure. There is a 4-dimensional cube that is parallel to the same structure. There is a 4-dimensional cube, okay? And okay, so yes, I'm gonna stop there just to make sure that we are completely confident with the structures that we're gonna be working with. Because this combinatorial notation is actually what gives the whole power of the proofs that we're gonna use that are very computational and combinatorial. Okay, so now let's put a probabilistic model here. Okay, so we're gonna start playing randomly with the n-dimensional cube, and what we're gonna do is we're gonna look at the graph. Topologically, we can also say the one-dimensional skeleton of the n-dimensional cube. And what we're going to do is that we're going to have the set of all vertices, and we're going to start putting edges randomly, okay? And how we want to do it, well, we want to include each one of the edges independently with probability P, okay? So good, and the edges we know that are the ones that have 1 star or 1 asterisk. Okay, so what is known about this random model in this graph? Well, Bertin, Ertes, and Spencer in 1977 and 1979 proved what is the behavior in the long run with respect to dimensionality of this random graph. So the most important thing for topology in this case is when it becomes connected, or one of the important questions. And so they proved that at the limit of when the dimensionality goes to infinity, the probability that the graph is connected goes to 0 if P, the probability that you are selecting, is smaller than 1/2, goes to e to the minus 1 if P equals 1/2, and goes to 1, so it's going to be connected with high probability if P is greater than 1/2. So anything that has more probability than a fair coin is going to allow you to have the graph connected, okay? So now immediately when one see this e to the minus 1 as a probability exactly at the threshold at P equals 1/2, so what happens at P equals 1/2? And well, actually Bertin and Spencer also proved that the probability of the number of components B equals to K plus 1 converges to the E minus 1 over K factorial. So it's a Poisson. Okay, so we're one-dimensional one-dimensional structures right now, and what we're saying is if we want to analyze the most natural random model here, that will be to put each one of the edges with probability p and with probability 1 minus p, don't putting the edge, and then independent each one of the edges from the other edges. And then we can select the probability between 0 and 1, and it's already know what is the threshold for the connectivity. Okay, so now, what happens when you have, let me compare it to another model that we know very well usually, and that is the Erdos-Rangy graphs. Okay, now you have n vertices, okay, and the number of edges is n choose 2 edges, okay. Then we know that the same probability, the limit when n goes to infinity of the probability of G being connected, goes to 0 if, and now we have a function with in terms of the number of vertices, if C goes to the minus infinity, and this is C, right? And then if C is any real number fixed, the probability that the G is connected when n goes to infinity is e to the minus C. And when C goes to infinity, then it converges to 1. So here the probability, the threshold probability is actually a function, and it's a function on n, okay? And this is not happening in the cubical case for the random graph, as we just see, as Erdos, Spencer, and Burtin proved. So we already are observing that topology is behaving a little bit different, or very different, when we change from the simplicial case to the cubical case. Okay. Any questions here? No? Okay. So let's keep going. Now, we want to jump to 2 dimensions. This is the promise of the title of the talk. So what happens with the topology when we are adding 2D faces? What could happen? Well, let me do one in the 3D case, okay? So let's say that I'm putting some 2D faces, and then I could, for example, form this structure. And this structure, well, for the topological point of view, you can say it's just S1, okay? Yeah, I mean, this is one thing that could happen. But you can also have only a wedge of circles, or you can have the cube, right? These are the 3 things that could happen. Okay, so, but good thing is that we are thinking on letting the dimensionality go to infinity. So before going to infinity, let us make a stop in the tesseract that is a 4-dimensional cube. So why is topology an interesting future to study? So which kind of surfaces could you embed in the 4D cube? And now I'm going to stop for people to answer in the chat. Which surfaces do you think you could embed if I allow you to use the 2-dimensional faces of the 4D cube? And I mean, I don't know if you have one at your home, or office, but could you name all the surfaces that you could make, that you could embed on the 4D cube? Someone has an idea? I mean, which one's your favorite surface?
A torus? No.
A torus, yeah. So let me, I have printed a torus, and then, you know, these 2 are actually equal. Yes. So a torus is possible to embed in a 4D cube, right? So this is how many faces you need. You need 16 faces. And yes, you get a torus here. Now, what other surfaces could you embed on the 4D cube?
A sphere?
A sphere, yes. And well, I mean, a sphere could be like this, like you have all the faces, right? But then for example, one could ask, okay, if I have a sphere, in how many ways could I embed a sphere? And in particular, how many vertices, edges, and 2D faces I will be needing for embedding a sphere. So let me show you some of the embeddings of the sphere. This is another one. Here you have, as you can see, this has different than the one that I show you here that has all the outer faces. So okay, so yes, so this is an example of another embedding of the sphere, right? And you are using a different number of vertices and faces here, okay? And this is another example, right? But then here you could actually see something. How many spheres, copies of the sphere could you independently embed here? So for example, you could embed 2, right? And then the thing is that if you really want to tell me how likely is to observe the sphere, you will need to actually calculate, know how all the ways that you have to embed the sphere, right? To tell me how likely it is to actually observe a sphere if I put randomly the 2D faces, and what is the difference that will allow you to say, okay, how likely is that with respect to how likely is to observe the torus, okay? So it is a combinatorial question. Okay, so I'm gonna start sharing my screen again.
We have a question in the chat.
Yes?
So the question is, what does it mean, the difference between the subgraph of Q to the N and the Erdős graph? Can it detect a problem using the computer for representing images? So I'm just reading the question and...
So let me, what does mean the difference between the subgraphs of Qn and the Erdős graphs? Can it detect problem using computer for representing images? Okay, so first of all, the difference between the cubical graph and the Erdős or the complete graph and vertices is a lot. Is the number of vertices on the cubical graph, it's 2 to the n vertices, and on graphs, complete graphs is n vertices. So, for example, that is one of the differences. It's very, very sparse, the cubical graph. I don't know if that answers the first question. Now, the second question, I'm not sure how to answer it, but because I don't understand exactly what it means using the computer for representing images with graphs, but we can go back to that at the end. Yes, so, okay, then let me switch my camera. Then it is important to know how easy is to have your favorite surfaces to be able to know how likely it is in the 4D cube to observe it, even when you are just placing the 2D faces with whatever distribution that you want, right? So we do need to understand completely the combinatorial properties of these if we want to give a precise probability of observing a surface. Now, of course, we will not do this for the long term in the sense of letting the dimensionality go to infinity. We're going to do something different. Okay, so, but I have a trivia here. Let me show you the trivia. So the trivia is, and people will get a 3D printed cubical Mobius band, is if you could find, and this is if you get bored in the talk, the smallest dimension of a cubical complex, or the dimensionality of a cubical graph, for being able to embed the Mobius map, okay? And also you need to give me the minimum number of faces needed for that. And then you will get a 3D printed cubical Mobius map. Okay, so let's see. Let's go to the random space that we actually want to study. So what we're going to have is we're going to have the one-dimensional skeleton fixed. So we have all the vertices and all the edges, and we're going to put the two-dimensional faces randomly. How? Well, we're going to mimic the models that we know in graphs. So we're going to include independently with probability P each one of the 2D faces. Okay. Now, which is the variable that we want to measure? Well, in this case, we want to measure the fundamental group. Okay. So, and this is why I said that it's very important to understand the combinatorial representation of cubical graphs and the cubical complexes that form it, because we're going to define the fundamental group in a combinatorial way. Okay, so we're going to define the edge path group, and for that, let me give you some operations that you can do with edges of the 2D faces. So we're going to say that this XY is equivalent to this CW if the 2D face is included, right? And then we're going to say that X is equivalent to ZWY if the 2D face is included, and we're going to say that ZYW is equivalent to CXY is equivalent to W if the 2D face is included. And also, if you have X and X minus 1, you're going to have the identity. So these operations are the only thing that we need to actually perform all the operations to calculate the edge path group. Okay. So we're going to fix the vertex that has only 0 entries, and the random edge path group is going to be the set of edge equivalent classes that we just defined of edge loops. So you're going to embed S1 that start at 0, 0, 0, 0. This the vertex that has only zeros in its entries, and then the product and the inverse are going to be defined by concatenation and reversal of edge group. Okay, and we just see how you can operate here. Okay, so going back to the example that we had before. So in this case, we have the random two-dimensional cubical complex. So this is the dimensionality 3. And then I run an experiment with some P, and this is the structure that we got. And then with this definition, we actually have that this edge loop can be deformed to the other edge loop. So we only have one element in the edge path group. Okay. Any questions here in this definition? No? Okay. So let's warm up and let's look at extremal cases. So what happens if I make P equals 0? If I make P equals 0, then the probability of having the 2D faces included is 0, meaning we go back to having only the graph, and we know how to calculate pi1 in this case. So basically what you have to do is you find a spanning tree of the graph, and the spanning tree will always have n-1 edges if n is the number of vertices. And so in this case, for example, for calculating the number of edges in the one skeleton of the 3D cube is 12, minus the number of vertices that we know is 8, and then you add 1, and then you know that then you have 5 copies of C for pi1 of this random two-dimensional cubical complex, but with P equals 0, so you have no faces. Okay. And then what happens in general for the n-dimensional cube? Well, the number of edges is going to be 2 to the n-1 times n, and the number of vertices is 2 to the n, the number of vertices in the n cube. And so you will have 2 to the n minus 1 n times n minus 2 plus 1 independent generators. And if you compare this with the total of number of 4 edges cycles in Qn, you see that yes, the number is not the same, as we all know, but just yeah, we need to use this formula, and only having all the 4 edge cycles will give us an upper bound, but not a very good upper bound. Okay, so by the way, this is very easy to calculate with the star notation. For example, the number of edges. So you know that you have 1 star in each of the in the entry of the vector, because edges are represented with 1 star. So you have 2 to the n minus 1, because you have only n minus 1 entries that you can put as 0 or 1, times n is where you can place the star. So this is why the star notation can be very useful for calculating. Okay, so this was p equals 0. Okay, if p equals 0, we already know how to calculate pi 1. And now what happens if p is bigger than 0, and of course strictly smaller or smaller than 1? So what happens with the random two-dimensional cubical complex that we get if we put each one of the faces independently with a Bernoulli with probability p? Yes, and of course, one of the things that we're interested in saying is, okay, at which p do we have pi 1 vanishing? So we want to find this threshold, ideally. Okay, and so if you want to remember what we have defined for pi 1, then pi 1 is the set of edge equivalent classes. Okay, so we're going to use yeah, this image a lot. Now, let me tell you what happens when we try to bring some intuition from the simplicial case. Okay, and so in the simplicial case, we know that we are working with a complete graph as the one skeleton. And the linear Machulan model that was presented around 2003, and I think the paper got published in 2006. So they introduced the two-dimensional simplicial complex, random simplicial complexes. And they proved that the homology group is the threshold for the homology group to vanish is 2 log n over n. So if you remember with the Ertas-Renyi graph, it was log n plus c over n, so meaning the threshold is log n over n. And then Kale, Babson, and Hoffman proved that the threshold for, or it's Rowley is not actually a sharp threshold, not yet, but they proved that it is the order of n to the minus 1/2. Okay, and of course there is a lot more done on these directions. It's not the scope of the talk, but I suggest you to look at the more recent results on this. But yes, so the point is, what I want you to take out of this is that homology and homotopy have different threshold functions and regimes, and also something very important here is that the threshold probability depends on n. Okay, in the two-dimensional case as well. Okay, so are there any questions? I wanna know if there are any questions. No? Okay, so let's keep going. Now, I'm going to define a relation that will allow us to actually say something about the threshold for pi 1 to vanishing. So the relations are going to allow us to analyze a local structure that we get when we look at three-dimensional cubes in the n-dimensional cube. So let's take x and y. There are 4 edge cycles, and we take a 3-dimensional cube. Now, we already know that if we have the other 4 faces of the cube that contains x and y, if that cube exists, then they're gonna deformation retract into one another, or they're gonna be actually the same element in the edge loop group. Okay, so this structure is a structure that we want to analyze. Okay, so we're going to have 2 different relations here that we're going to use very much. The first relation is, yes, I have 2 4 edge cycles that are related by the existence of a 3D cube that contains both as parallel faces. Okay, and the other relation that we want is not only that, but actually the other 4 edges are there. Okay, so here's an example of a case that x and y will not be related with respect to having all the other 4 faces present. Okay, so one question would be, how much can we say about pi 1 if we study this local structure only observing 3-dimensional structures? Well, let's try to play a little bit with only the 3D cube, but for that, let me define a general graph for all dimensions. So the vertices are going to be the set of all 4 edge cycles. The edges, we're going to put edges if we have the 2 edge cycles that are parallel, right? And if the Hamming distance is 1, okay? And if they have the stars in the same entries. Yes, so if this happens, we're going to put an edge between the 4 edge cycles. So we're jumping a little bit here in the sense that we're building a graph out of the 2D complex, cubical complex. Okay, so let's do some exercises. So let's take this first cube, and let's say that we have A, B, and C as 2D faces, and X, Y, and D are not there. How am I going to build this graph that I'm referring to? Well, I'm going to have vertices. We have 6 vertices because there are 6 4 edge cycles. And then I'm going to color them if they already have the 2D face. Okay? So here I'm coloring A, B, and C because A, B, and C are there, and I'm not coloring X and Y and D. Okay? So let's do the other example. So we have X, B, Y, and D included, and A and C are not there. Well, we have the first 1 vertex per each one of the 4 edge cycles, and then we put a color if they're actually, if the 2 face is included. So I have X in green, I have B in green, Y in green, and D in green. Now, why do I have an edge between A and C? Because if I look at A and C, they're parallel, and the other 4 edge cycles had a 2D face, okay? And so here you can compute what is happening in this cube. But basically, in this cube, you have 5 faces, 5 2D faces, and you have only missing D. So what will happen is that everything could deformation retract to a point. So pi 1 should vanish here, okay? And yes, it's easy to see that building the graph. So you're going to have 6 vertices. You're going to have X, A, B, Y, and C in green. And then what's going to happen is that D and B are going to be connected by an edge. And because B is in green, it's going to spread to D. Okay, good. So let's see. So this building this graph is the most important thing for the proofs of where the threshold is for pi1 to vanish. Is there any question there? No? Okay. So now let me tell you the nice thing that we prove about this graph. So the graph is going to have n choose 2 components. Each one of the components is a Q1 n minus 2. So you have a dimensionality n minus 2, and then you have the one-dimensional skeleton. So you have the graph of n minus 2 dimensional cube. And another thing with respect to the distribution that you get in this graph is that it's going to be a random graph, and it's actually a random graph in a cubical graph. And so we recover the Burtin-Erdos-Spencer random graph here, and the good news is that we already know that the threshold for connectivity of this graph is known. And if we have the graph connected and we have one of the 2D phases present, then everything deformation retracts to a point in that component. So how will you use this known result? Well, you have to set the P so that you can use it with the result from Erdos Burtin-Spencer. So let's fix P bigger than 1/2 to the 1/4. And then the reason is that for being able to have to deformation retract 2 48 cycles that are in a 3D cube as parallel, is that you actually need the other 4 present, right? So this will be 1/2 to the 1/4. Okay, and the lemma is that if you select P bigger than 1/2 to the 1/4, then each one of the components is going to be connected. And indeed, so the proof goes select P star equals P to the 4, because you need to have the 4 phases and they're independent. Then if P is bigger than 1/2 to the 1/4, then P star is bigger than 1/2 to the 1/4 to the power of 4, and then P star is bigger than 1/2. And then we can use Burtin-Erdos-Spencer to tell us that the graph is going to be connected. And if this graph is connected, then we get that pi1 vanishes by construction. But what is the value of P here? So the value of P here is around 0.8, okay? And then you could ask, okay, is this the right threshold? And when we were asking this, we started running experiments, and everything was pointing out that the actual threshold for pi1 to vanish is P equals 1/2. So we ran some experiments, and we were absolutely convinced about that. And actually, the experiments were completely based on the puzzle graph that I just described. Okay. Any questions there? Good. So now let's define an algorithm based on this. And this algorithm is going to allow us to use the fact that we could actually add some 2D phases once we know that some 2D phases are already there. So what happens if you have the 5 2D phases in the cube, and we want to calculate pi1 there? Well, pi1 is going to be the same there, and in the full having the cube, right? So this is important. This means that if I can add these 2D phases because pi1 is not being altered, then I can actually have more 2D phases when I'm calculating the graph, right? And so this is going to give us an iterative algorithm for finding contractible 4 edge cycles. Stage 0. So build the graph of parallel 4 edge cycles. Stage 1, you need to spread the coloring, the green coloring that you saw, that is each one of the vertices is in green if you have 2D phase at the beginning. And you do this in each one of the components. We saw that you have n choose 2 components. And then in stage 2 is you bring inside the 2D faces that were newly colored. Okay, so now you have more 4 edge cycles. And then you go to step 1. Okay, and you recalculate. And if you do this, you're gonna see that actually the graphs that we just construct are getting more edges, and so it is possible to have the color spread in more vertices. And the question is, when n goes to infinity, when the dimensionality of the cube goes to infinity, if this algorithm will ever converge. So is it gonna stop at some point? And so this is the main theorem actually that we prove, is that if P is bigger than 1/2, then this parallel homotopy algorithm finishes in 3 steps with high probability as n goes to infinity. So this was this was unexpected, to be honest. We thought that perhaps it was going to finish in more iterations, or even that the number of iterations was going to grow with n. But no, only 3 iterations, and then you have pi1 vanishing. So let me restate it in a computational way, because this is how the computational experiments told us that P should be 1/2. So what you do is you program in such a way, the algorithm in such a way that what you do is you put each one of the 2D faces at the beginning, then you do the step 2, you build the graph, then you spread the color, and then you redo it, okay? And then you stop the algorithm at the point where the color got spread to all the vertices. Yeah, and yes, it will stop with within 3 iterations. And now you could ask me, wait, but how far do I have to go in dimensionality to actually observe this? And we were observing this even for d equals 11. So already the 11th dimensional cube was telling us that it should be 1/2 the threshold. Okay, and then what happens when you are at 1/2 or below 1/2? Well, if you are at 1/2 or below, then you will have isolated edges with high probability. And isolated edges are those where you don't have any 2D phase that is incident to the edge. So of course, this already tells you that pi1 cannot vanish, but in this case, it is, the threshold coincides. And that this is theorem 1. Okay. If someone wants to prove this is, I think, that P smaller or equal than 1/2 has only isolated edges, is a very good exercise if you are studying the book of the probabilistic method. Okay. So this is the main theorem, as you said. P equals 1/2 is the threshold for pi1 to vanish. Now, one thing that you could ask is what happens when P is smaller than 1/2, right? We want to say a little bit more. And we were able to prove that actually if P is greater than around 0.28, then with high probability, you will only have copies of C as a decomposition of pi1. And actually the number of copies is going to be the number of isolated edges, meaning that the only obstruction that you get if you select P between 1/2 and 0.28 are going to be isolated edges. Nothing else is happening. There is no toruses, no nothing with torsion, and yes. So basically, if you are above 1/2, pi1 vanishes. If you are between 1/2 and 0.28, the only obstruction that you get is isolated edges. And then we could ask of course, what if I want some particular surface? For example, the torus that we already know that actually is possible to do in the 4D cube, or yeah, just take your favorite surface, even if it is oriented or not, and then you could ask yourself, what if I want to be sure what is the P that I need to select so that I can assure that I'm gonna observe this structure. And then, well, we were able to prove, for example, for the projective plane, that if P is less than 1 to the minus 1/2 to the 1/40, that is around 0.017, then Z over Z2 is a free factor of pi1 with high probability, meaning you will be having copies of the projective plane there. And okay, so where is this 40 coming here? And this is a nice thing here, and is, well, if you observe here, what we have here is actually a projective plane, a realization of the projective plane in the 5D cube. Okay, so you can embed a projective plane in a 5D cube, and this is one of the ways of doing it. This has 40 edges, and because you don't want these edges, I mean, you can assure that you're gonna have a free factor of pi1 and Z over 2Z if you can assure that the structure will not have more 2D faces coming to the edges. So you need the probability that this will happen. So 1 minus 1/2 to the 140. Okay, so you need to isolate each one of these edges. You need to make these edges that only have these 2D faces. And this is actually a conjecture that we're almost about to prove, that there is no torsion with high probability if P is bigger than 1 minus 1/2 to the 140. So this is, yeah, hopefully we're going to be able to prove it soon. And then, well, I mean, the torus also, what you do is you know that you need 2 to the 5 edges. There is the number of edges that you have in the representation that I show you, and then you could ask, of course, for other structures. And yeah, the important thing is, okay, if you find the minimal representation of the surface that you want to ask, well, not the threshold exactly, but that if P is less than this probability, you will actually observe it, then you need to look for the minimal surfaces. And this is why the extremal combinatorics of finding minimal representation of surfaces in the D cube are important. And yes, so that was all, and the talk in a nutshell. Then we were playing with the complete one skeleton of the D-dimensional cube, where we were adding 2-dimensional square faces, IID with Bernoulli P, and this is the analog model to linear Mosulin on the simplicial complexes. And we proved that if P is bigger than 1/2, then with high probability pi1 is trivial. If P is less or equal than 1/2, with high probability pi1 is no trivial. And also we know that the only obstructions are isolated edges. And for example, you could ask different groups to be factors of pi1, and we saw the examples that we saw was torus, projective plane, and yes, we also found the representation of the Klein bottle, so we also have like an upper bound for that. And yes, the conjecture that we think that 0.017 is the threshold for pi1 to be torsion free. And yes, with that, thank you very much. That's it for questions.
Thank you very much for the very colorful and interesting talk.
Not, I have the question of what is the minimum embedding of the Mobius band?
Yes, you gave that question to us. So do we have any conjectures concerning that? Anybody with any ideas? So you promised a model of the 3D printed Möbius band if somebody guesses the correct. So we have a guess here. Would that be 3?
Where will you place the, so you have the 4D cube, right? Where will you place 3 2D faces to generate the Möbius band?
So
With only 3.
it seems not. 3 is not enough.
Yeah, so now no one will get it. I will get it. I can keep it to my office, but I'm going to show it just to not let people go with the empty hands. So it's 6. And you can see here, you start here. Then you go like this. Okay. Then you need this face to go up. You already are here. And then you go like that, and then you go back. It's a little bit messy. You can, and I think I'm going to upload an ant walking here that I'm going to work with Manuel Esteves so that you can see that it is actually a Möbius band. But the answer is 6 is the minimum to have a Möbius band on the 4D cube. Yes.
So nobody gets the 3D model. Too bad.
Yes, too bad.
So do we have any more questions for Érika?
I'm sorry, I was assuming it is not going to work. That's why I was writing. But yeah, thanks for the great talk.
Yeah, thanks. Thanks for coming. Thanks everyone for coming.
So thanks very much, Érika, again for the talk. And if there are no more questions, I would conclude the session with one big applause for Érika.
Thank you very much.